talk to you about is something related to machine learning, but mind you, here, all I know about machine learning I've learned this week, and I wrote this presentation last week. But I'm a mathematician, and it would be rather pointless for me to talk about mathematics here. I mean, two mathematicians, so I want to convey some ideas and some questions that I might have to the other members of the audience, so I hope the mathematicians among us have a good book with them. So some of the goals we have, or I have here, is to build some bridges between theory and practice now that we have people of different backgrounds here in the same room. I might utterly fail, but at least I'll try doing something a little outside my comfort zone. And this means, in practice, describing how deep learning or some kind of machine learning might help experimentalists and theorists learn from each other. And, well, of course, I want to learn some things that machines might be able to teach me, but also I might have something to give to those who want to implement these methods. So one of the things that will come up is finding reliable ways to reconstruct as much information as possible from the spectrum of free oscillations. So this is a concrete problem that I want to phrase my ideas around, so as to give something concrete. And the most important goal is you guys telling me whether any of this makes any sense. Okay, so let's start with the actual problem. So I've prepared a substantial amount of material, and I will not be able to cover all of that, so it will be completely fine if you interrupt me at any point and ask or make comments. So the problem, first let's see what the free oscillations are. So like any elastic object, like a drum, the earth can vibrate, and these vibrations are known as free oscillations, and they are excited by earthquakes. So just like you can hit a drum and you can excite the normal modes in a drum, you can do the same for the earth, but you just have to hit your earth with an earthquake. And the amplitudes of these different modes in these oscillations will vary from event to event. And I'm not interested in the characteristics of individual events, I'm interested in the characteristics of the planet. So the frequencies are the things that I want to look at, not the amplitudes. Okay, so the set of frequencies is the spectrum of free oscillations, and that is the data that I will be considering, at least in theory. And just to give some numbers, this may or may not be correct, but maybe about 10,000 first frequencies are known, so that we have a substantial amount of data that we could actually use for the Earth. Then of course, when we go to another celestial body, we will have substantially less data available. Okay, so my point of view is rather geometrical, and that is one of the messages that I want to drive through here. So the classical point of view is that elastic waves do not go straight if the medium is inhomogeneous. So if there are changes in the sound speeds, then the elastic waves will bend one way or the other. But the way I see things is that they go straight in a curved geometry. So I demand that my waves go straight no matter what, but the inhomogeneity is seen as non-Euclidean geometry. So now compare this to what happens in the theory of gravity. So the old view from Newton is that the Earth is on a curved path because of the force exerted by the sun on Earth, and therefore the Earth doesn't go straight. And the new view is that the Earth goes straight in a geometry that is influenced by the sun. And I want to have this same kind of, say, Einsteinian view of elasticity to see it as a geometrical thing. And I believe that's a beneficial point of view to have, at least occasionally. So in this elastic geometry, the important thing is distance, and the distance is travel time between any 2 points. And all the other geometrical quantities, so it might have angles, volumes, areas, whatnot, they can be derived from this concept of length. So there's one geometry for each wave speed, so if you have actually several polarizations, then there will be different geometries, and in the very simplest cases, you might have a separate B geometry and an S geometry. But I will do scalar waves without any polarization just to keep things simple. But mind you that if you do a fully realistic model, then things would be far more complicated than what I have here. So the problem would be, does the spectrum of free oscillations determine the geometry? So the geometry would be the end goal, what we want to construct. And this problem is hard in theory, so it's very hard to prove any kind of uniqueness. And it's going to be hard in practice to do it reliably, partly because it's non-unique, but I will discuss that non-uniqueness in a moment. So the meta problem that might be more interesting here today is that how can theoretical and practical endeavors with this actual problem benefit from each other? Because we have people here that might be interested in different sides of the same question. Okay, so spectral inverse problems like this one is, we have a spectrum and we want to recover some data from spectral measurements. They tend to be hard, and this one is not an exception. So therefore it's a good playing ground. So what we would like to do is reconstruct the geometry in the Cartesian coordinates, because we have these kind of natural physical Euclidean coordinates. But unfortunately, this is impossible in anisotropic elasticity unless you have very, very severe constraints. Because the elastic model is simply kind of blind to the Euclidean geometry and it can't see what it is. But that is a kind of benefit of the geometrical point of view, that you can encode this kind of blindness to your model very easily. Okay, so once one has reconstructed the elastic geometry, one would then like to interpret it physically and chemically. What does this variation in the speed of sound with respect to position and direction actually mean? And I believe it might be beneficial to separate these two steps, to decouple the problem into first finding the geometry and then making an interpretation. Okay, so that is kind of the problem itself. And then we have a little mathematical result with Martin and Vitali. So let me first describe what the model is. So a very large class of anisotropic linearized elasticity can be modeled by a Riemannian manifold with boundary. And actually a general Riemannian manifold is not general enough to cover all elastic phenomena, but this will be enough for this talk. I won't be going any further. So I have a spherically symmetric Earth, which will be the unit ball, and it doesn't really matter that I have the unit radius, it's just the coordinate radius for convenience. And then I have a Riemannian metric, which is the Euclidean metric E multiplied by some factor, and that factor is the negative second power of the sound speed, which only now depends on the radius. So that means that the thing is spherically symmetric. And in fact, if you have this ball here, and you have a rotation invariant Riemannian metric, then there is a diffeomorphism of the ball so that it pulls this thing back into this particular form. So in fact, what we are looking at is the most general rotation invariant Riemannian manifold, for those who have interest in these classification theorems of this kind. Okay, so the modes of the free oscillations are now modeled as the scalar Neumann eigenfunctions of the Laplace-Beltrami operator of my manifold. So the scalar here just means that I have no polarizations, and that's a bit of a cheat, but that's something we'll have to live with here now. So reconstructing a Riemannian manifold from the Neumann spectrum of this operator is more or less, at least morally, the same thing as reconstructing an elliptically inhomogeneous elastic object from the spectrum of free oscillations. So elliptic inhomogeneity just means that the directional dependence of speed of sound is ellipsoidal at any point. Okay, so we'll need to make some geometrical assumptions on our planet. And the geometry we have is all encoded in the velocity profile. And that sound speed will have to satisfy a condition which is known as the Herklotz condition. And it looks like this. This kind of derivative has to be positive. And it doesn't make much sense at first sight, but just to get a rough idea, it just means that the geodesics, that is the straight lines, that is still lines along which these seismic waves travel, will curve outwards so that they are not trapped inside the planet, and they will make their way up to our measurement stations on the surface of the Earth or whatever celestial body we happen to be studying. And we also need some regularity assumptions, of course, to be able to prove anything. And the thing is that whatever we assume, the Earth is not going to be satisfied. So there's a Prem model. It is not exactly smooth. There will be jump discontinuities in both pressure and shear waves. And the shear wave speed will vanish in the liquid outer core, or rather you might argue that the whole polarization does not exist there, but either way this will be a bit of an issue for the geometry, which is kind of non-existent in part of the manifold. So apart from these problems of jumps and liquids, both the shear and pressure wave speeds actually do satisfy the Hertzsprung condition everywhere, which is rather convenient to live on a planet which seems to satisfy our assumptions to a large extent. Okay, so now in this kind of context, we have a theorem. So now suppose M is the closed unit ball in a three-dimensional space, and I have a family of radial sound speeds. So remember, I had a sound speed depending only on the radius, and now I introduce an additional, completely artificial parameter S. And sound speed is smooth, and it satisfies the Hertzsprung condition and the very weak generic geometrical conditions that I will not entertain you with. But the thing is that now if I vary this parameter, and I assume that each one of them gives rise to the same spectrum, so that I make an isospectral deformation, I deform my spherically symmetric manifold without changing the spectrum, then the conclusion is that I can't change the manifold at all. So this kind of thing is known as spectral rigidity, so this very simple model of the round Earth is actually spectrally rigid. Okay, so we'll come back to this in a simpler form later, but there are some limitations that are important to know. So the first thing is that none of our proofs actually work without spherical symmetry, but the result may well be more general. And that is actually what we expect, but we are unable to prove anything yet. And our model only includes p waves, or rather scalar waves. So if you had a full model, you should include polarizations, as I mentioned before. And we have these liquids, and there are interfaces, and the interfaces mean that the real elastic geometry is actually non-smooth. So you have to study, for example, Riemannian manifolds that have certain kinds of conormal singularities. So studying elasticity brings you to exotic differential geometry, which is rather surprising at first. So the proof works with strong assumptions, but maybe the same auxiliary quantities, maybe the same ideas might be a useful thing to look at. And things to look at is the kind of the important things that I want you focus on next. So I want to talk about these deep structures of a planet, so not the surface structures, but something far deeper, by using deep learning or whatever kind of machine learning architecture you might have. So, of course, to construct the deep structures of a planet, any of the planets, we want to use more than just spectral data. There will be one kind of data that is available, but there will of course be much more. So these mathematical models that we have, like the theorem that I presented, these solutions to universe problems and any explicit reconstruction algorithms, they are always simple-minded. You have a single type of data and you reconstruct a single quantity out of that. And that is of course far from the reality. You can only prove things about toy models. That's just unfortunately the state of the art. So all data can of course be used together in an algorithm based on machine learning or iteration or what have you. But the thing is that if you do that, it's rarely provably reliable. So we don't really have any proofs that it should work or it will converge or whatever. And that makes the result maybe a little less trustworthy. So maybe there are some useful quantities to look at. So in some cases, the spectral data is enough to reconstruct the geometry. So our theorem gives a very weak version of that. So yes, using full data, all of the data we have would lead to better results, but maybe only the sub-algorithm using only the spectral data will have theoretical support. So, well, why not then apply that sub-algorithm? So use whatever we can do reliably from partial data, and then use that as data for the machine learning algorithm. So that's just a decent guess we can make in a reliable way, and that is useful data. That might not be our final result. But this useful data doesn't really have to be a good guess at the eventual object. It can be anything. So it could be something far less final, and we don't even really need to know how to use it. We just need to have a hunch that it contains useful information, and then the machine learning method will hopefully make use of it. So the question is, what are useful and reliably computable quantities that we might want to pre-process out of our data and throw at the machine that wants to learn? Of course, it will take the machine a lot of time to learn things that we could trivially give it to it. Okay. So recall the result we had. which says that isospectral deformations of a spherically symmetric Riemannian manifold are trivial. This is paraphrasing the earlier one in simple words, or simpler words. So in a very weak sense, in spherical geometry and spherical symmetry, this means that the spectrum of the free oscillations determines the geometry. Okay, and here's a little quick outline of how the proof goes. If you want to see the details, you can download my slides online and see the actual full proof given in much more detail. But the first thing we do, we have the eigenvalues, lambda 0, lambda 1, and so forth. And from these, we compute a function like this, ft. So function of time, just define a simple series like that. And that series will actually converge in the sense of distributions, and it will fail to be a smooth function. But anyhow, and that is formally the trace of this kind of operator. Okay, and that is why I call it the trace function. So then we see where this function has singularities. And it turns out that the singularities of this function are more or less precisely the length spectrum. So the set of lengths of periodic paths that reflect on the surface of the planet. And now when we have this kind of length spectral data and we linearize it, it leads to something that we call the periodic broken ray transform, and that transform can be inverted explicitly. So that is our proof. But the important thing here is the points 1 and 2. So we can construct a function like this, and the function, and especially its singularities, will contain useful geometrical data. We don't really know how to use that data when we don't have spherical symmetry or when we don't have smoothness, but either way it will be useful. So useful quantities to look at is this function and the points where f behaves badly. And that will lead you to the length spectrum, and it might also be accessible in other ways. But maybe these would be useful things for a machine to look at, even if we don't know how to use them in an explicit way. So, for example, we want to find the length of an interval given its Neumann spectrum. So now I have just a one-dimensional planet because I want to do something very simple and explicit. So if the length of the interval is L, then the eigenvalues are given by this simple formula here. And now I suppose the length of the interval is 1/2, and then we have measured these eigenvalues, and I want to recover this number 1/2. Okay, so what we do is we compute and plot this trace function. Now, of course, in this case, we do something far simpler, but I just want to illustrate this idea at work. So here's the interval from 0 to 1/2, and here are the 5 first eigenfunctions. So the first one is hidden because it's just a constant 1. And what a periodic broken ray would mean here is you start from the left, go all the way through, and make your way back. So the shortest one has length 1, and then of course you can do the same thing twice, meaning you will have length 2 and length 3 and so on. So starting with only 5 eigenvalues, you can compute the trace function, and it looks like this. Very little information, and you already see very strong singularities precisely at 1, 2, 3, 4, and so on. So this might be a good way to compute from spectral data something geometrical, and the singularities are precisely at very geometrical points. Okay, so the singularities give the length spectrum, and in this case, it's rather trivial to determine the geometry, that is the length of the interval, from the length spectrum. In higher dimensional cases, it will be harder, but it's something that the machine might help us with. So perhaps the trace would be a useful thing to extract from machine learning with spectral data. So the singularities do contain some geometrical information, and the geometry is the thing we want to reconstruct. So perhaps that would be a good approach, and perhaps other theorists would have other potentially useful quantities to throw at a machine and improve performance. So mathematicians tend to be a little shy with their kind of ideas that go into their lemmas, and they want to promote their theorems, but in practice it might be more useful to look at the ideas behind the proofs than actually the theorems themselves. It depends. So what happens here is that we will have a certain kind of data blow up. So we will have multiplied the amount of data we have by offering the machine a number of possibly useful quantities. And of course, some of our guesses will be bad. Some of our ideas will be useless, as always. So some of the promising things can be less promising after use. and the learning process can be unnecessarily or even unfeasibly heavy if we use all of the ideas we have. So the problem is, can a machine learning algorithm tell which parts of the data it eventually needs? That would be a great thing to have. So it would have a couple of effects. One is that the process is lighter if it only does what it needs to do. That's rather obvious. The second one is we don't need to collect expensive but unnecessary data, so this would help us improve designing experiments. So data can be very expensive, for example, on Mars, which takes a little bit of effort to bring anything on top of that planet. And thirdly, theorists would get hints of what quantities are actually useful to look at, because we can prove something in special cases, but it doesn't mean that the same ideas are useful at all in more generalities, and we would like to have some hints. So for example, we don't know whether the trace function is useful in more complicated spectral inverse problems. We kind of think we know that it is useful, but we don't know exactly what is the geometrical data contained. And if we might have more insights from a machine, then we would be able to maybe proceed a little faster with our mathematical endeavors. So that brings me to something that I want to call deep teaching. So the goal of this meeting is that people from different fields would share insights. And the goal of this talk is that theorists and experimentalists would share insights on what are useful things to consider when trying to solve a problem. So for example, to extract structural information from spectral data, well, maybe you should look at the trace function and its singularities. This is a very concrete suggestion that maybe construct this object and look where it fails to be smooth. And deep teaching, on the other hand, so if the machine learning algorithm learns what data is useful, it can tell it to those collecting data and those working with the theory. So the machine, after learning, might hopefully be able to teach us. So different forms of machine learning can produce algorithms that perform brilliantly well, as we have seen here this week. But performance is much like intuition. The machine just knows. So the problem is, can a machine have not only intuition but also understanding? And that is something that we have heard talks about this week, and it's a hard problem, but it's something that would be significant also for mathematicians trying to prove new mathematical theorems. So understanding to me means the ability to communicate ideas to humans, because eventually we want to understand. It's not enough that machines understand. The problem is, machines can learn, but can they pass on what they have learned to us? So we'd like to see this happen at various different scales. So with this specific inverse spectral problem, in geophysics in general, so many of the people here in this room will be interested in, and of course in machine learning at large, to kind of make it more useful for the other kinds of scientific endeavors we have around the same ideas. And I suppose this is where I want to